Hello, and welcome to some extra examples from section 10.3. Hopefully the first PDF helped you a little bit, but I wanted to do a couple of them that are related to your homework here, just to show you how we can apply the integral test and when to apply the integral test. So these are actually both odd numbered questions from the assignment, so they might look familiar if you've already done it. First one is number 31. This one, excuse me, tends to create some problems for people. And we're dealing with this weird sum with 1 over n in the numerator, then log of n, and then the square root of log of n squared minus 1. Don't let the fact that this starts at 3 fool you. That's just because if n was less than 3, then the natural log would be less than 1. And then the square root wouldn't make sense. So they're just trying to make sure it stays defined. But those first few terms really don't matter in terms of convergence or divergence. When I see the logarithm in there as well as the 1 over n, I start thinking integral test where we would take u to be log of x because the derivative of the log is 1 over x. So let's go ahead and start that. So we rewrite it as an integral, and again, our theorem says that if this integral converges, then so does the series. Okay, again, we take a u substitution. U is log of x, du is 1 over x dx, and we get this integral, changing the boundaries, log of 3 instead of 3, and notice as x goes to infinity, so does u. So we still end up with an integral with an infinite boundary. And so we get this weird 1 over u times root u squared minus 1. And this is where we have to challenge our memory. Again, writing it as a limit. And you have to remember that that hopefully looked a little familiar. You go back and you look in your integrals, it's probably not one you have memorized, but that is the arcsecant. So we get the limit as we approach the infinity of the arcsecant evaluated from log of 3 up to b. Plugging those numbers in, you get the limit as b approaches infinity of arcsecant of b, and then minus arcsecant of log 3, that's some number. Now, the inverse secant, that's 1 over the cosine. So 1 over the cosine has to head to infinity. That means the cosine has to be going to 0. And if we think, okay, what angle has a cosine of 0? That's pi over 2. So we get pi over 2 minus the inverse secant of log 3. The actual value isn't what we're interested in. What we're interested in is that it does converge. We actually do get a value. So therefore, since that integral converges, we get that that series also converges. Okay, let's go up to the next odd problem, which is number 33. And here we have the sine n equals 1 to infinity of n times sine 1 over n. Now, I'm suspicious because this n is out there in front that the terms likely aren't going to go to 0. So again, we don't have to do everything using integral test in this section. We have geometric series facts, we have the P series, which we've developed, and we have the integral test. So use the other tests as well. In this case, I'm going to look at the nth term test. Again, nth term can't show convergence, but it does show divergence. And in this case, I just strongly suspect that the terms aren't going to go to 0. So let's go ahead and check that. So take the limit as n goes to infinity of n sine 1 over n. This is one of those weird infinity times 0 cases because sine 1 over n is going to 0, n is going to infinity. So we have to write it as a fraction to use L'Hopital's rule. So I'm writing as a sine of 1 over n over 1 over n. Taking the derivative on top and bottom, you get the cosine of 1 over n times the derivative of the 1 over n, which is negative 1 n to the minus 2. And same in the denominator, the derivative of 1 over n is negative 1 into minus 2. And notice you get cancellation there. And all that we're left with is the cosine of 1 over n. Well, as n goes to infinity, 1 over n goes to 0, so we get cosine of 0, which is 1. So in this case, we can say it diverges simply because the terms don't go to 0, and there's no need to work through any nasty integrals or the integral test. That's one thing we're going to have to work on in the coming sections, and I will continue to post more examples, because looking at a series and then deciding, okay, which of these tools do we use is actually the hard part. That's all for this time, and we'll start into the next section with the next video, and that will be the beginning of 10.4. Hope your day is good.